Okay, now I'm recording a step 2.
Hello, everybody, and welcome in the next episode of our Prague seminar for mathematical physics. We are very glad that our invitation has been accepted by a new postdoc researcher in our institute, Vincenzo Emilio Marotta. I hope I guessed it correctly. And Vincenzo allegedly is going to talk about something interesting about T-duality and some insights how to connect the T-duality with relations in the category of Courant algebroids or something like that. So something like that. You specify the time. It's Vincenzo, thanks for coming and the floor is yours. Thank you.
Well, I gotta say that I feel a bit shameless coming here and talking about Courant algebraic relations, right? Because it's mostly based on math work or like using the law of these results. And yet, I'll try to discuss pretty much a different approach to some objects that we generalized isometries and how to modify slightly their definition to allow some relations to be actually isometries for these modified objects. So far, I said nothing. But this is going to allow me to discuss from the point of view of exact Courant algebroids what it means to have a T-duality relation. How am I going to do it? Well, pretty much I would like to start from saying like just talking for a couple of minutes about what is T-duality. And well, the honest answer would be I don't know. Otherwise, I would be studying it probably. But the idea is consider like a sigma model. And for me, sigma model is just going to be pretty much given by a manifold M together with a metric G and say closed free form H. Okay, so H is a closed free form on M and G is a Riemannian metric. These are going to be the target space of your sigma model. And these objects are going to help you to define an action functional on the space of smooth functions from a surface with a pseudo-Riemannian metric into M somehow. I'm not going to tell you what, how, or why, because I will just care about the geometry of the target space. Okay. So whenever I say sigma model, just think of these three objects. What happens? Or maybe it's too small.
Maybe
I'll try to write it. So what people do in physics when they think about T-duality? They consider like M to be a principal G bundle, okay, where G acts on M via isometries of G. Okay. In particular, they have a procedure that's called gauging that somehow allows you to redefine your tensors, mixing their components. I'm not going to tell you how or why. There are important examples for like, through the Busher rules in which you can mix this thing to an H. It's not only closed, but it's also exact. And you obtain a different tensors, let me call it G prime and H prime, defined on potentially a completely different manifold, which might have completely different topology. What does it mean in terms of geometry? Well, the answer is I don't know. But I'll try to argue that this actually represents a Courant algebraic relation under certain assumptions and in certain circumstances. And hopefully I'll try to draw a parallel with what happens with another famous T-duality, which is called Poisson-Lie T-duality, which somewhat is similar and yet different to the things I'm going to talk about. So far so good concerning sigma models, I think. Told you, just keep in mind as a punchline of this talk, pretty much that this correspondence here is going to be some sort of generalized isometry for some exact Courant algebroids that I'm going to define throughout the talk. Okay, so how do I erase here? This one. Just to set the notation, I'd like to start from just a definition of exact Courant algebroid, just because I want to give you my notation, not bigger. I mean, you know all this better than me. So, definition: an exact Courant algebroid is going to be a vector bundle E over M endowed with a symmetric bilinear pairing, non-degenerate bilinear pairing of fiber-wise, an anchor row, which is just a vector monomorphism over the identity from E to Tn, and a bracket and its space of sections. And these three objects have to satisfy three conditions. First and foremost, row of E1, E2, E3 equals to 1 plus E2 it's not big enough, right? Very good. Then this bracket is not skew-symmetric, in particular, like its symmetric component is pretty much defined, controlled by this object. E1, E1, and 3. Well, I'm just going to. Okay, so these are like the three objects you need. In particular, like mixing these conditions give you a fourth property that is like the anchored lightly through, which pretty much looks like this. E1, where of course, like here I should say that E1, let's say EI are just sections of E. So you just have the anchored lightly through the towards plus row E1, E2, and you also have that 5. If you actually mix this with the Jacobi identity, that let's say row of your bracket, I mean, pretty much the anchor is going to be a bracket morphism with respect to the. This is just the Lie bracket on Tn. Okay. This is all you gotta know, all you gotta need to pretty much understand what I'm saying, up to some more objects that I'll try to define. If you're not familiar with this, maybe a standard example is going to be this. Algebroid, which is pretty much given by the width sum of the tangent and the tangent bundle over M. The anchor row is just the projection on Tn. And the bracket is going to be given by this construction, where this guy is the Lie bracket within vector fields, Lie derivative along x3 elements, H, where H again is a closed 3 form. Okay, so you can start, reminiscing what happens, why I wanted to discuss sigma models in terms of Courant algebroids. Of course, this closedness comes from the fact that this bracket has to satisfy the Jacobi identity. If you just look at it. So this is the standard example. I will refer to it standard probably. Don't remember, just ask me again.
Can I ask a stupid question? I'm a bit confusing. Like the bracket of E2 and E3,
The
on
bracket,
the left-hand side of the equation of one.
E2, E1, E3.
No,
Yeah.
the left.
Which one?
The other side of the equality. Yeah.
Here it's just the pairing of these two guys, and this like the Lie derivative of this function along this vector field.
So then this is the thing and say this is a vector field in the tangent.
This is the
differentiating.
Then you take the Lie derivative of this smooth function
Okay. Yeah.
over.
That's fine. Just didn't understand.
Okay. Sorry, bad notation probably. Anyways, this is like the basic construction that we have. I actually have to introduce one more object that is like, well, a class of objects probably, that are called exact Courant algebroids, that are just given by the following. Pretty much notice that we can obtain a map rho star that is given by going from T star ending to E by composing the transpose of rho with the music isomorphism given by the non-degenerate symmetric linear pair. Okay, so this gives you a map that goes from T star N into E and actually defines a sequence. If this sequence is short exact, the one just writing, then we call the Courant algebroid exact. Okay, this is quite interesting because these objects are actually classified, classification is similar, and pretty much the construction. So this map is rho star, the one I just told you how it's defined, and this is rho P. Pretty much what you can do is that the classification is based again on the existence of, well, on the rank homology of these three forms, pretty much. Because whenever you choose a maximal isotropic splitting of the short exact sequence, but it's sigma, you can obtain H, obtain this closed three form defined by these objects. Sorry, it is sigma of X, sigma of Y, sigma of Z. Okay, this is a closed tree form, and actually, if you happen to say, okay, well, what happens if I change the splitting? If I go to another maximally isotropic splitting, well, the difference between those two splittings will just end up being a two form, which means that this guy is just going to be shifted by the differential of the two form, and the homology class of H just doesn't change. So exact random algebroids over M are classified by the rank well, the Schiller class, or like the rank homology that you can actually find up there. Yeah, and after this, I think you actually really know everything you need to know. And this leads me actually to the second point that I would like to discuss, which is going to be the key ingredient to my talk, which is reduction of, actually, I should say isotropic reduction of exact random algebroids over Fourier manifolds. How does this work? Oh, this is just it. Okay. Then let's use this. So let me consider again E as an exact run. From now on, M is always going to be, besides smooth manifold, always going to be connected. I don't want to have troubles with anything. And I'm also going to define. I'm going to suppose that I have a subbundle K of E that is actually isotropic. Okay, and such that rho of K, rho of K perp, perpendicularity defined with respect to the symmetric bilinear non-degenerate pairing is actually equal to Tn, the whole of Tn. This can be done, exists. And well, I need to define definition, basic sections. What are basic sections of K perp with respect to K are just objects such that this happens. You take the bracket, whatever the K of E, this is going to be a section of K. Okay. In particular, you can one can show an interesting property about these basic sections, that is the following: if basic sections pointwise span K perp, then you have the following properties, that is every bracket of sections of K and sections of K perp actually lands again in sections of K perp. And you actually have another funny property, that is K is actually involutive with respect to the Dorfman bracket. So this weird bracket that I go here. Okay, why do I need this thing? Well, because at this point I'm going to assume that rho of K, well, actually is going to be a regular distribution on Tn. It's integrable because rho is a bracket morphism, as we discussed before. So this gives like a foliation, I'm going to call like curly F of the base manifold, and I'm going to assume that the quotient, the leaf space of the foliation, so the quotient of M with respect to F, is actually a smooth manifold. What I want to discuss then is, are there like conditions under which Q inherits an exact Courant algebroid structure from E, so E defined on M? Well, yes, there are. And this leads pretty much to the statement of the following here. That is to, I'd say, to most things about Canticle theory, but I'm going to present it in the version given by Zambon, Michael Zambon, and goes as follows. Okay, let me be a little more precise. So as I said, I'm going to suppose K is isotropic. That satisfies that, and I'm going to assume that so basic sections span pointwise paper. This is the key assumption for the theorem to work. I'm going to assume that this is a group manifold. In particular, you know that there exists a unique surjective summation from N to Q manifold phi. And then, pretty much what happens is that then there exists a Courant algebroid derived over Q such that you have the following pullback diagram of vector bundles, which is given by K first mod K as a bundle over M. Is going to be here E over Q. And this is actually here phi. Okay. Why will I need this? Because this is going to be a key ingredient in order to discuss how sigma models are related. And what do I mean by sigma models? And at this point, it's worth mentioning that as you
Just a question, is K over K actually a pullback bundle or not?
yeah, no, this actually,
So it's
they're
universal.
literally fiber-wise isomorphic here.
Okay, so it's universal.
Yes, exactly.
So it's really,
It's really well
it's
defined.
not a pullback of.
Yes, actually, and the quotient here is literally well defined because of the existence of basic sections. Pretty much the identification you have, the good identification you have of fibers is given by the fact that two elements of the same leaf in K perp mod K can be identified if they actually are elements, take the value of basic sections in 2 points of the same leaf. That's actually a well-defined identification because you can, since the Jacobian it holds, you can have the adjoint action well-defined over vector fields that connect. Elements in K that then map into vector fields that connect these 2 points. And then you integrate it and you get an actual isomorphism that give you a very good, well-defined identification. But anyways, these are a bit technicalities. Maybe you don't care. The point is, this construction is going to be crucial. It's going to be crucial for the rest of the talk, and we'll probably give you as well like an example of how a Courant algebroid relation might work. Actually, let me give you one more statement. Actually, I should give you an example, in particular about what are basic sections. So let me consider, like an example, the reduction of Tm direct sum histogram. Okay, and I'll just take K to be TF for some foliation of M, then I'm assuming to be endowed with this space. Okay, actually, technically I should write it like this, but anyways. So who's K perp? K perp is just going to be given by Tm itself. Direct sum the annihilator of TF, obviously. So what are the basic sections? The basic sections are going to be exactly the projector given by elements in this form. X, so basic section. They're going to be given by elements in this form. B of not we start with, where X are projectable vector fields with respect to the foliation F. And here, like in order to span the annihilator pointwise, you just need to pull back functions from the base manifold.
So right, very interested the question, what capital F?
Capital F is just, here is the foliation of N. I'm just taking F to be a foliation of N.
Arbitrary or
Sorry?
arbitrary.
In this case, it's arbitrary, yes. Okay. I just, arbitrary in the sense that it still has to satisfy this. And that needs to be well defined in the sense that Q, the leaf space of the foliation, needs to be smooth. That's the only assumption I make. So this is how the basic section works. So this is a projectable vector field with respect to the foliation, and the annihilator is going to be spanned by pullback of functions from the base. So F is just okay. So since we define we have a well-defined notion of of reduction over foliated manifolds for exact random approach. Well, can we reduce subbundles somehow, subbundles of E to our E-rect, to this exact random algebra? We might. This actually resulted is hidden somewhere in Zampon's paper, but if you dig enough, you can actually find it. And it's actually going to be, let's say, that is given by this thing. Suppose you have a subbundle E. At this point, actually, I didn't mention it, but all the subbundles I'm choosing are supported on M, on the whole of M. Even though the original statement of the theorem is over any submanifold of M that then can be foliated itself, and then you can take push. But I don't want to go that deep. I'm just going to stick to this formulation of the theorem. So let me suppose that W is a subbundle of E such that I have that the whole reduction picture holds. So all the assumptions of this theorem hold. Then we're going to have, and let me also assume that W intersection K perp has constant bracket. Okay. If sections of K, sections of W end up to be sections of W plus K, then there exists W red, which is a vector subbundle over Q of vector subbundle of E red. That is as well supported on Q. Okay. A funny thing about this that I'm going to read in the following, that this assumption takes a nice form if K is included in W, which is included in K perp, then this assumption simply reduces to be the obvious thing. This reducibility of this specific kind, this special kind of subbundles is going to be needed in the future because I want to define some optics that have K as some sort of symmetry with respect to the Courant bracket, to the Gaussian brackets. Okay. All right. Okay. Once I stated this, once we have that this picture holds, I should define one more notion. I know it's a lot. I need quite a lot of machinery to state something that is pretty much given by the existence of adapted splittings of the Courant algebroid E that allows me to have this reduction picture. Okay. What do I mean by that? I want to have splittings of that exact Courant algebroid that actually descend to splittings of E red. So the reduced Courant algebroid is, of course, doesn't always happen for any splitting. I need some specific assumptions that are pretty much given by the following. So again, definition. The assumptions are always the same. This picture after all. So sigma going from Tm to E is adapted if the following holds. Okay. One. The image of sigma is isotropic. Two. Sigma of Tm plus E K perp. 3. For any x, Tm that is projectable in the sense that I just discussed. Sigma of x is actually a basic section of K perp. So the lift by the splitting of a projectable vector field is actually basic. It has to be well behaved then with respect to this procedure, right? In particular, this actually gives you, you can actually show that these objects have some more properties, which are rho of the image of sigma intersection with K perp is actually double of Tm, which is fair to assume. In particular, this is actually obvious once you assume that rho of K perp is actually the whole of Tn. And I showed you in this example that K perp pretty much has Tm as well in there, if you want to go to the standard case. So this is like fairly clear assumption. And the important assumption in which we can claim this proposition is that what happens is that sections of K, sections of image sigma intersected K perp actually lands in image of sigma plus K. Okay, so what does it mean? Again, this is pretty much the key property that tells you that sigma is going to descend two-way splitting of E-ray, because you're going to look at this and obtain the image of sigma, which was intersection here with K perp is constant rank, pretty much satisfies the assumption of this proposition, which means you have an isotropic subbundle of E-ray that can actually be seen to be the image of a splitting of E-ray. It's just a machinery that you have to do some tricks and calculations, but it happens. So these objects are like well behaved with respect to the reduction procedure. Okay. I will leave them in the future. It's where I'm not trying to make you fall asleep at this point with a lot of notions, and it's a lot to process, but I'm going to need all of it and maybe more. At this stage, then I can finally, well, actually, yeah, maybe I should. It's also worth mentioning that using these adapted splittings, you can literally check conditions under which the reduction procedure works. So, for instance, what happens here if I just do the reduction of the standard case, and I'll, with the bracket classified by that closed free form that I told you about? Well, the only condition you have for this reduction to happen is that ix of h must be equal to 0 for any x in here. What does it mean? Pretty much, since h is closed, we're just saying that h must be basic with respect to the formation. So if it descends to the quotient, this is just going to be the pullback of a tree form on the basement. The funny thing is, in the general case, the definition that I gave you before of h, that I raised because I'm an idiot, actually descends to a well-defined h by applying the construction of an adapted splitting. So you just can map both, can map the construction. So for h of the original Courant algebroid, it would be the pullback of h defined through the reduced adapted splitting, if that makes sense. Okay.
So maybe can you say it once more? So with yeah, I'm sorry, I'm slow.
No,
H is so when you have an adapted splitting, then H, which is a free form of
yes.
bundle, descends to be a free form of manifold.
Well, that you have it in general,
okay.
Because for instance,
yeah.
This happens in the standard case. But what you can actually see is that by definition, you end up having that h, your h, x, y, z that I defined before as the bracket of
right.
sigma x, sigma y, sigma z. Actually, if you use the definition of adapted splitting, you can see that this thing actually, I'm not going to introduce more notation for sigma red, but you can actually see that this is actually equal to the pullback of a sigma red, pretty much. It's so well behaved that you actually have all the notions you need compactly defined in this picture. And I'm going to use all of them again. So yeah, I guess enough of introducing material, but I really need to do it. And now I can start introducing the relations of Courant algebroids. I'll do it try to do it very quickly and maybe stop in it, but one motivation for introducing them could be that, well, as you can see, as you probably guess, vector bundle morphisms, in this case, in order to discuss objects that map brackets into brackets of Courant algebroids, so they preserve the bracket, are a bit complicated to define. First of all, if they're over any smooth map, even defining an isomorphism of C infinity modules over different managements, it's actually a very complicated thing. What I mean is simply this: like, if you actually, even if you have this picture for any two vector bundles at this stage, where this map phi is just a smooth map, well, how do you define an isomorphism or like even a morphism of these two space of sections? One is a C infinity modules, the other one module one is a C infinity and two modules. Module, there is no way of pulling back functions because phi is smooth. That's a bit of a problem, even at this level. I will not even mention what happens in the bracket. I mean, it doesn't happen. I think Mackenzie found like a nice trick. to have a modular morphism if you actually assume that this guy is fiber-wise bijective. But again, it is not going to help us that much. It helps us in the case of.
But it can be done.
It can be done, yeah. It definitely can be done. I mean, it's quite a pain in the ass, if I may say, but you can do it. For the algebroids, for instance, that's the case. You actually have a well-defined note as well. He has a well-defined notion, even the product morphism, and it's actually slightly smoother, like slightly easier to do. But then, yeah, the idea is that one can introduce some more general objects, and well, let's try to do it. And I'm not going to mention all of this, but the idea is going to be. So, again, definition, let E1 and E2 be Courant algebroids. Okay, any Courant algebroid, they don't need necessarily to be exact. And let me introduce the following Courant algebroid, another example. It is pretty much given by the product of these two guys. So I'm just going to consider like E1 cross E2 as a Courant algebroid over M1 cross E2. Okay, where again, the anchor is pretty much just given by two anchors. This guy, then I guess you got the gist of it. Like the inner product is just going to be given by, let's be a little bit more careful here. One composition of projection one, so over the first plus two, projection two, and the bracket. Well, again, the bracket is just up to opposition of the two brackets of the original quadrant. Okay. So what is the relation between these two objects? Well, a relation between these two objects is a subbundle. Where what is this guy? Well, this guy is simply is this thing, but with a minus sign here, pretty much. So let me talk about this one. It's a subbundle of this guy that is supported on a manifold C, on a submanifold of M1 cross M2, that satisfies some assumptions. The first one, it must be R is simply isotropic, and two, we have the compatibility with the anchor that I basically talked about for K and K part. So that R, so we are, so the row of our third is actually equal, so not equal, sorry, but just in EOC, right? Sorry, potentially equal to TC. And this is what you need. In particular, like, a special case is going to be when C is actually the graph of a smooth map between these two manifolds, which is going to be relevant to us, in particular, if you want to describe this guy in terms of relation, show that this is not true. Actually, that E red and the original Courant algebroid are actually related. So we're actually gonna use that notion, and yeah, actually, why not? Let's try to do that. I think at this point it's actually helpful to show how they work. I might discuss, for instance, like how the graph of an isomorphism of Courant algebroids is a relation, but maybe it's just gonna be wasting time. So let's try to show a slightly non-trivial example of Courant algebroid relation, which is actually the one that I just mentioned. Okay. So how do we do this? So keep in mind that now this picture holds. We're in this picture, and my claim is simply that E and E red are related by the relation that I'm going to define for those. which is actually, I'm going to define it point-wise, actually, maybe, because, thank you. I need one more layer of notation. Let me do this map. The map that goes from K first to P red. This is over. Okay. This is a vector bundle map over the surgical submersion. I'm going to use it here for any E in a curve at the point P. Okay, so P is for any P on P. It's clearly a bundle. Okay. And well, now we have to show that QK satisfies his assumptions. Well, you can see that, for instance, this is supported.
Sorry, isn't there some compatibility, some evolutivity missing or something?
Yes, I forgot to mention the important one, the bracket condition, which is very true. R is avoided. Fair enough. I forget about the important things in life, as always. So yeah, this is supported on the graph of this projection here. This one, the subject distribution here, which is clearly a submanifold of M plus. Okay. So, how do we show that this thing is actually a relation? Well, I'm not gonna go through all the proof, because also like it's pretty much based on Jan's proof of what happens for the reduction of G equivalent algebroids, so I don't need to do all of the job. But yeah, you can easily see that this thing is isotropic with respect to this pairing. Well, pretty much because the two pairings actually on E red and on E, well, one descends from the other. So if you just do the machinery, it's just gonna be a trivial calculation to see that this is actually isotropic. Let's say the only technical, slightly more technical bit that we need to prove is this. But it's not too hard as well. I'm not going to do it just because it's time consuming. And what happens about the condition that I forgot, the volatility? This is pretty much granted by the fact that the bracket, the Dorfman bracket of two basic sections is actually basic again, which is a property that you're going to need if you just want to show that, yeah, these objects are again part of this game. And yeah, that condition pretty much follows from just from using the Jacobi identity and the property that controls the symmetry of the Dorfman bracket. But yeah, and it's just mirroring again what happens in the case of G equivalent Courant algebroids. Because in that case, basic sections are just going to be your invariant section with respect to the G action. That's the bottom line. So yeah, again, this is your first example, or at least in this talk, of a Courant algebroid relation, and I'm going to need this one very much. I might need to spend like just a few words on how Courant algebroid relations compose. I'm not going to say much because it's a rather technical thing, but the point is, what is how do we define the composition of these objects? So let me suppose that you have, I'm not going to say much about this. So suppose you have, say, R, a Courant algebroid relation from E1 to E2, and R prime algebroid relation from E2 to E3. Then how do we define the composition of R prime? We just write this. Okay. We just consider E1 and E3 to be in E1 plus E3. Of the change product such that you have the E1, E2 in R and E2, E3 in R prime for some E2, E. Okay, so this is what needs to happen. Unfortunately, this is not a relation, at least not yet, because this is clearly a subset of E1 cross E3 bar over line, but this fails to be a submanifold as yet. But actually, thanks to Jan's work, pretty much, there's all the theory discussed and played out, which pretty much tells you that you don't have to worry too much, but you have to check some conditions. First and foremost, how do you show that this ends up being a vector subbundle of E1 cross E3 supported over a submanifold? Well, that's a pretty complicated task, but there's a theorem that helps you. That is the Grabowski-Rekiewicz theorem that says that whenever you have a submanifold of a vector bundle, and this is invariant under like scalar multiplication, then this ends up being a vector subbundle supported over a submanifold of the base manifold. This theorem is super powerful and is pretty much the crux to solving this problem. I'm not going to say more because it gets, well, I will have to introduce more objects. But this leads pretty much to having some regularity conditions of different intersections of submanifolds. And I might claim at some point that I'm going to use them, even if I don't show them. Okay? So trust me on that if I ever get to that point. Okay, so this is for compositions. So one more object that I need is given by generalized metrics. Again, fairly well-known object with well-known notion. And in my case, I will consider a generalized metric to be simply a subbundle V plus supported name of a micron algebroid that is positive definite with respect to my variable. Okay, so this is a generalized metric, and I should probably write it as generalized. Okay, so this is the definition of generalized metric. This is maybe one of the two equivalent definitions of generalized metrics. Well, what's going on? Well, at this point, I would like to talk to you, well, what is a generalized metric? Well, you can, in the split case, you can always think of a generalized metric, and in my case also, base manifold, I said from the beginning, is connected.
So it was just remarked, like, you should also assume that it's maximally positive.
It's maximally positive, yes. Again, just important things. So yeah, say that the rank of the plus is pretty much rank. Yeah, well, I cannot do it because I didn't. Well, if E is exact, and let's assume that E is exact because this is going to happen, then this guy's going to have after rank, and then you're going to be happy with that always. But you can do it for any signature, for any signature of E. I just don't do it at this point. So if you want to think of V plus in terms of the standard Courant algebroid, you just end up thinking there's a nice result that tells you that V plus is actually equivalent to a Riemannian metric on the base and the 2 form on the base. Okay? So whenever you think of V plus, this metric and 2 form combine nicely to give you a Riemannian metric, pretty much a fiber-wise Riemannian metric on V. Okay? So since I talked about relations, since I discussed metrics, well, what is a well-defined notion for an axionomy of these objects? Okay, well, then let's try to get one and maybe discuss a little bit about it. So, again, definition. Let R be a. I should have used a better notation for this, guys. They're not morphisms. R be a Courant algebroid relation supported on C, submanifold 1 cross 2, and let V1 plus and V2 plus be generalized metrics, okay, respectively on E1 and E2. And well, let me also define Vi minus, this is just the orthogonal complement of Vi plus. And then let me define the following subbundles that are going to be given by V, this curly V minus These are like subbundles clearly of E1 plus E2. Then generalized, we go doctor, geometry plus. Then R is a generalized isometry for V1 and V2 if pointwise the following thing holds. So for any P in C, you have the following condition. R of P equals to curly V plus P intersecting with R of P direct sum V minus P intersected R of P. So this is going to be my pointwise definition of a generalized isometry. Unfortunately, I cannot make it global because, well, this intersection might be very wide with R, and I have no way to know. The rank is not going to be constant, but pointwise this works. This, unfortunately, is not the original definition of generalized isometry. But it's not the one, not the original definition. But I think I can spend like a few minutes talking about that. This definition and the original definition are equivalent, and this can be shown somehow, but I have to give you the original definition, which is the following. So we have definition, well, this is another one. So this is not the most, maybe not the most general definition of generalized. In particular, like, when you want to introduce generalized metrics, you usually assume that you have an automorphism E, an automorphism of E over the identity, such that it squares in the identity on E and is a Riemannian metric. Okay, this is totally equivalent to this. Well, under the assumption, I guess, that M is connected. Otherwise, you might have problems probably. And pretty much what you end up having that tau clearly has two eigenbundles, one with a +1 and
You don't have to assume that it's connected.
Oh, no, okay.
On every component.
No, on every component you define it well. Yeah, okay, fair enough. Thanks. So what you end up having is pretty much a D plus is going to be the +1 eigenbundle of this automorphism. That's course the paper. And by using, well, this property, we can at least argue that the two definitions are pretty much equivalent. In particular, if I give you then the, if I need to answer a lot of things, if I can give you the original definition of generalized isometry, okay?
Or you can use the other blackboard now.
Yeah, I'm lazy. No, you're right. I probably should, but I only answer this. It's gonna be okay. So, where are you? Okay, so this is the original definition, and we have the R again is a random algebraic relation supported on C, and consider like tau1 and tau2 to be generalized metrics respectively on E1 and E2, and then define tau to be again a tau to be like an automorphism of E1 cross E2, pretty much. Then a generalized isometry, you have that. Is a generalized isometry if the following holds, which is pretty much the tau of R equals to R. Okay. This is simpler than that one. But unfortunately, I'm going to need in the following this definition, because starting from this definition, I can argue of a definition of a different object that includes some invariance condition with respect to a subbundle. Anyways, no spoilers. Maybe I can quickly argue why these things are equivalent. Well, pretty much because you can define the eigenbundles of tau to be pretty much in a similar form to V plus minus, and then if you just take any element, you can pretty much always decompose E1 plus E2 in these two eigenbundles, which are just going to be B plus represented B minus. This is, I still didn't assume that they are in that form, yeah? So I can always decompose R in Rp as R equals to R plus R minus. Okay? So if I do that and then apply tau of R is going to be R plus minus R minus. And so we have the pretty much R plus and R minus following the definition, and R plus minus and R minus are both elements in R. Okay? Fair enough. So what I mean is that this again, this is an RP and this is both. Okay? So what we have is pretty much that R plus and R minus again are in RP, and so we pretty much have that RP is included in B plus P plus B minus. Okay? Sorry, no, stupid me. Yeah, no, R plus, I said this is in RP, this is in RP, so yeah, this guy is actually included in this guy. This P, this section, R plus. Yeah, and this is one way. And well, yeah, the other inclusion is for free, so you don't have to argue. And you also can do the converse. I'm not going to do it because, well, I guess I'm running short on time. But anyways, this should probably, hopefully, convince you that these two things are the same. Or like, at least they are two different aspects of the same. So, what do we do with this? Well, what do we do? Well, first of all, again, I would like to show you an example of a generalized isometry. So the best I can do at this point is show you when a relation fails to be a generalized isometry. In particular, the only relation that I discussed a little bit about, which is QK. So the relation coming from the reduction of Courant algebroids. Even in this case, in particular, because we have isotropic reduction, that relation fails to be a generalized isometry if I actually assume that I have generalized metrics on the original Courant algebroid and the reduced one. Okay, so why is that not like a relation? So if you remember QK, this pointwise used to be this guy, E sharp and natural E for E paper. Okay, E, of course. So let me suppose that I have a generalized metric tau on E and tau red on here. Okay, those are generalized metrics. Well, how can we conclude that they are not, that this is not a generalized isometry? Well, let's consider the product. Okay, this object applied to QK would also give you, if this was a generalized isometry, you should have this. We don't know. So what actually happens if you do it? Let's use this definition. For any element of QK, it's just going to be doing like this. So we have the first element is static for E. The second element is going to be static for E. Such that E is going to be sloppy with notation because of the number. So for this guy, in order to be in here, we must have that tau sharp of E actually equals to sharp of tau of E, right? For any in paper. But let's look closely at what happens if E is not only in paper, but it's also in K. Okay? I mean, K is isotropic, so it's always in paper, no problem. So what happens if this happens? If E is in K? Let me consider this. G of E. This is clearly, positive, cannot be negative. What happens? You have E of tau of E is non-negative, which means that tau of E cannot be in paper. But tau of E must be defined in paper if sharp wants to act on it. Otherwise, it's not defined. This paper, and this cannot be a generalized isometry. Okay, so this is like a quick argument to prove that this is not a generalized isometry, and this motivates me, like just to look for things that will allow this Q of K to be some sort of isometry. Clearly, at this stage, I don't want to change the assumption of isotropic reduction. So okay, I still want it to be isotropic. So the only thing I'm left with is changing the definition of generalized metric. I want something different. What is this going to be? Well, luckily I didn't do the job, but Scherer and Strobel did and introduced another notion that is the one of transverse generalized isometry. And what I'll be able to do at some point is to show that actually for transverse generalized isometry, this QK represents some sort of isometry. Okay, but I don't think I have enough time to go into that. This trick. I'll try my best to be quick. So. Is everything clear? Like, any question? I don't know. Any questions from that standpoint? Maybe many, maybe more. So, at this point,
Maybe I have a question. So we proved that not any isometry, sorry, in a reverse direction, not every relation is the generalized isometry.
No.
So
no. Well, you need more definitions. You need a little bit more. You need for them to be satisfied actually one of the definitions. So it's actually quite a stringent position. But actually, one thing that generalized isometry usually do is actually well behaved under composition. So if you compose them, you can actually not have an algebroid isometry, which is not a bad thing. And for instance, like the kind of isometry I'm going to introduce is not as well behaved under composition as generalized isometry, because well, you have somewhat more freedom. And so this makes things a little bit messier and more fun. Anyways, let me again give you a definition, which is pretty much the one that transverse generalized isometry. So E again is going to be an exact Courant algebroid over N. And let me fix K to be involutive, isotropic, subbundle. Fragmentation, but never mind. And again, let me take W to be a subbundle E, which is again maximum. So it has to have rank of W is pretty much rank of E. Now I'm defining it for exact rank algebroids as well. So this thing, W, in order to be a for W to be a transverse generalized metric, we need to have two conditions. Well, first of all, actually three conditions, sorry. One, if you remember this guy I told you about before, so you're gonna guess what's gonna be one of the conditions. Two, positive for any W that is not in K. Okay, so if I take any element in W that is not in K, the inner product restricted to that part of the subbundle has to be positive. 3. Guess what? There's going to be an invariance condition with respect to the Dorfman bracket, which is exactly the one that I told you about before when I was discussing reduction of subbundles of an exact Courant algebroid. Okay, so this is actually invariance condition. Okay. In particular, what happens if you want to picture this, say in terms of the well, I told you at some point that the generalized metric is a pair, right? Given by a metric and a 2-form on the base manifold. Well, here you pretty much have the same thing, but you're just allowing for degeneracy. So the idea is that if you look at the split case or the standard case where you have Tm direct sum T star m, those two components, those two tensors, are just going to be well defined as before, but you just have to take them in particular. Well, you just have to take them to be degenerate. One caveat should be that rho, in order to do so, rho has to be injected when restricted to K, if one should be technical. But under the assumptions of the reduction that I'm taking, this is actually a byproduct of the reduction procedure. So the existence of that kind of reduction procedure actually allows me to show that rho restricted to K is always injected. So I get it for free if I assume that reduction holds. So what does this mean in terms of that G pair G and B? Okay, in particular, let me take it as this. W, if you take in this case, W is just going to be like the graph of G plus B for symmetric G and a 2 form B. Okay, and what happens? Then what's going to be your K? K is pretty much the kernel. K is involutive, right? Did I say that K is involutive? I did not say that K is involutive. No, I didn't. Okay. So K is just the kernel of these two guys. And actually, if you look at it in this case, it's just going to give you again the tangent distribution gives you a foliation of the base manifold again because of involutivity. And what does this guy mean? Well, this guy just means that when you actually spell out the calculation with respect to the bracket that I wrote you at the very beginning, you end up having that L of x of G equals to L of x of B equals to 0 for any x in here. Okay, and one more condition, of course, is on H. So H is basic with respect to the foliation, but you expect that because somehow this thing is screaming reducement pretty much. So the idea is you have invariance condition of the background with respect to the foliation plus, well, one interesting condition that allows you to reduce this guy whenever the leaf space of M, the leaf space of my foliation F is moved again. Okay. So this is the basic object that now I want to deal with. So this is just a couple. And what's the idea? Well, the idea is to define some sort of isometry for this guy here. But I'm not happy with just an idea of isometry. What I really want to preserve is this. But I want to preserve the bit in which the sum of G and B is non-degenerate. I would like to have a notion that allows me for the definition of isometry that actually does not necessarily preserve K. Why? In the split case, again, if you want to mirror an example, K is just going to be, again, it's just going to induce a foliation of the base manifold. If I actually assume a stricter general notion of isometry for this object, I always end up having, for instance, for an actual isometry in which there is an isomorphism involved, that the foliation is going to be preserved. Okay, so if I map W1 over E1 and W2 over E2 by an isomorphism of Courant algebroids, and I impose that the whole of W must be really preserved, I also will end up having somehow that the foliation, so K1 and K2, have to be preserved. I want to allow for a notion that is slightly more general than that. Well, or at least that it includes that, but it does not necessarily preserve the invariant, the sub-bundle that defines the invariance of this object. It might sound like a silly notion, but it actually ends up being crucial when you want to discuss changes of topology in the reduction, in this reduction procedure. Should I go on? Because I guess it's, I think I can stop and then, that's the point I've seen your it's honestly, I think it's 1 hour. This is too much for everybody. So I guess in the next episode, I'll tell you about these isometries.
Next time, yeah?
Yeah, exactly. Yeah. I think.
Next week.
What did I stop? Time for questions.
I think at least one, right? You don't know how the story ends. Yeah.
We have to cut.
Yeah. See, I love my audience.
I guess it's another one question. Maybe I missed it, and maybe it's really for next time. So you're is it like a isotropic, but not maximal isotropic kind of?
No, this is not maximal isotropic. K don't have to actually. No, I don't want K to be maximal isotropic.
Yes.
Otherwise, I would end up with G and B being trivial.
Yeah.
So no, this has to be only isotropic. And in general, I will never assume maximal isotropicity of K for any of my reduction. Otherwise, what I just end up having pretty much nothing. So yeah.
Yes. So it's like a. So there's a property of isometries that you need this degeneracy.
Yeah, I don't want, the idea is that I will not want to preserve the degenerate bit.
Yeah.
Because that is a bit too restrictive for what I want to do. In particular, when I want to show, well, it's a bit restrictive for many reasons. Some of them I'll tell you like in the next time. But one of them is definitely that, when I will end up trying to tie the knot for T-duality, remember I told you about the background metrics I can have. Well, somehow I want these guys to be lifted to a bigger manifold. And when I can lift them, well, it also means that QK is going to be a generalized one for those objects. And then I want to map them over to another parameter, right? And then I want to quotient again. And I need this notion to be a little bit weaker than a standard generalization object. In particular, if I allow for the reduction to be isotropic. If I wanted to do non-isotropic reduction, and I'm still thinking about it, I mean, I don't know yet how it works in the case of foliation, but it should be well behaved as well. Then maybe there's a chance of being able to mirror what happens with Poisson-Lie T-duality, which I think that non-isotropicity is crucial. But yeah, in this case, and well, I'll tell you more next time. Like, when I draw a nice picture, and hopefully it'll make more sense.
It's based on already existing article, or?
Look, don't look at me. The job, this is fault. No. Yeah, it's pretty much, as I said at some point, it's the Antwerp and Strobel and Schedera. A bit for the definition of transverse generalized entry. And
But basically, all ideas in my paper are actually ideas of Paul Scheller.
okay. And then blame
Paul is the
it's always spreading.
Always.
Let's put it okay.
one who started everything.
No, but still, I guess, yeah. At least the main tools, main technologies in Jan's paper, then Strobel and Schiller are just for this definition. And yeah, then applications are going to be in different flavors, some coming from physics, some coming from, say, so-called topological T-duality, which is something I would like to discuss, at least if I manage to. And yeah, that's pretty much it. Well, thank you.
So any other question? I told Brian stretching. So if not, we would like to thank you again.
The TV series.